Hello, people. I hope you. What do I hope? I don't know. Oh yeah, the. I hope you like that demonstration today, the rodeo demonstration. I dig it. Right, great physics there. So our look at. I'll just back up. Our look at. What's up, buddy? Hey, come on in.
Alright, I just wanted to let you know, I was waiting to tell you if I could go to the tournaments,
Yeah.
but I can go there for the 4th,
Great.
the one on the 4th.
Great.
I won't be around for the one on the 11th.
All right. That's actually. I mean, that's good because we need midfielders.
Alright.
Hang on one second. Whoops. Um, let's see. Yeah, so horizontal circles. You know, the thing about these, the questions that we look at with objects moving in horizontal circles, the speeds will always stay the same. All right. You know, the two hard ones are these. This is a typical sort of car on a curve one. Here's the car on a curve one. All right, where you'll be asked to find three things, one of three things, either mu or v or r, and you'll have to be given the other two. But notice that mass doesn't matter. And notice here, free body diagram is a must. All right, so the car on a curve, which is really like this one, you know, as long as it's friction, I call that car on a curve. As long as friction is providing the centripetal force. Here, this is the other horizontal circle one that's tricky, and it's I don't know what you call this one. There's a problem in the notes. There's a ride. There used to be a ride at the Great Escape. I think it was called the Gravitron or something. Or the Rotor. It's called the Rotor. It was awesome. Um, but this one where it's friction up and normal in, this is the other tricky one. So, but um, the free body diagram is really the key here. All right, so these, not too bad. Okay, these horizontal ones. Again, these are the two hard ones. Now, when you get to vertical circles, things get a little tricky. All right, so let's look at, say, a roller coaster loop. And what we want to be able to do is really analyze forces in three different locations. All right, so yeah, we're sort of getting at that thing. If we look at the top, well, if we look at the forces acting on this object, there's always going to be an mg, all right? And I'll just put that right in here, the same everywhere, right? The Earth pulls down on the object with a certain force mg. Now, at other places, there's got to be a force that points inward, right? Here, it's normal force. And notice how big I drew it. I drew it larger than mg. And it has to be that way because, as we know, for an object that moves in a circle, the net force has to be towards the center. Or I should say there has to be a component of net force that points towards the center. Right? Only way for that to happen here is if n is larger than mg. If they are equal, it means the object's in equilibrium and will move with a constant velocity. That means it won't be able to change direction like we know it constantly does. Okay? At the side here, well, we get a normal force that points in like that. At the top, I'll draw a small one because, you know, it doesn't have to be bigger than ng. It could be. It doesn't have to be. All right, because we definitely have a net force inward just from mg. All right, so if we do this, you know, I guess what I'm trying to get at here is let's do a net force statement at each location. All right, at the top, now again, the centripetal direction means positive is in, negative is out. Okay, so at the top, we'd say mg plus normal is mac. Okay, you know, we actually don't do any. Come on, there you go. We actually don't do any analysis really of the object at the 9 o'clock position there at the side. But top and bottom are the two places we will look. And at the bottom, again, if we do net FC MAC, this is going to be N minus MG equals MAC. I kind of wish I wrote it up here as N plus. All right, notice here at the bottom, MG points outward. It is in the negative direction. All right, so you know, the deal is, in order to have some centripetal acceleration, you know, this says that, well, you know, normal can be whatever you want. Here, in order for AC to be positive, we need normal has to be bigger than mg. So I'll just say here, normal can be anything. Anything positive, right? Normal's not going to point outward. But as long as normal is literally anything, well, mg is positive. We'll get a positive centripetal acceleration. All right? But here's what happens. You know, at the top, there's some what we call, magic speed, sort of magic speed, where you feel weightless. All right? And that's kind of like saying, well, if we put a scale under your butt if you're sitting in some roller coaster car, remember what scales measure? Scales don't measure your weight. Scales measure normal force. All right, bathroom scales measure normal force. So there's actually, if that seat doesn't have to push on your butt, then you feel weightless, right? So what we're getting at here is, if we say you feel weightless, that means that normal force is 0. And notice, up here, we can get away with having normal force of 0 because mg still points towards the center. mg provides is the entire centripetal force. So if we look for that special speed and just say, well, it's mg is mac, or mg is mv squared over r. Look, it's the same speed for everybody. Doesn't matter what your mass is. If we get that roller coaster at just the right speed, which again depends on the radius of the loop, there's some speed we can write as gr, where you feel, square root of gr, where you feel weightless. Make sense? Here's some more what we call apparent weight problems, right? And these might be in a different order in your slides, my apologies. I think they're in the last slide, maybe. All right, so here's Tarzan swinging on a vine. At the bottom, he feels like he has to pull hard enough to support 3 times his weight, or he feels like he weighs 3 times what he really does. Let's find his speed. So here's, let's see, here's Tarzan swinging on this, in this arc. At the very bottom right here, well, what forces? There's a tension force. There's an mg. Okay? And let's see, net Fc equals mac, or T minus mg equals, I'll write it as this, mv squared over r. Now notice, I haven't really, I read the question quick, but no matter what the question asks, I'm going to do this, right? I'm going to draw a free body diagram. I'm going to do my net force in the centripetal direction statement, and then we can see what the question asks. Now here's the deal. This is, he feels like he weighs 3 times his weight. Well, we said, apparent weight is typically about normal force. In this case, it's about the tension force, right? Notice this. He feels like he has to pull hard enough to support 3 times his weight. All right, so we're saying that T is 3 times his weight. Ouch. Ouch. Fair enough there? That's the only real trick. So this is 3mg minus mg equals mv squared over r. Or 2mg is mv squared over r. Doesn't matter what Tarzan's mass is. Find his speed. V is the square root of 2 gr. So that's a square root of 2 times 10 times 10. Square root of 200 is, anyone? 14 and change, right? Yeah. I think 14 squared is 196. So about that. Fair enough? Here's another one. Car drives over the top of a hill at 25. So here's, let's see. Here's our hill. Car drives over this hill. And the hill is almost like, part of a circular, it's got a section of it that's part of a circle. So here's the car up here. Driver for a moment feels like she weighs only 1/4 of her actual weight. Well, here is her weight. And we get this force upward that seems like it's a quarter of her weight. Right? This apparent weight thing, in this case, yes, is the normal force. Okay? So, net FC, MAC, or mg minus n is mv squared over r, mg minus mg over 4, mv squared over r. So this is the, come here you, the whole weight minus a quarter of the weight, so that's 3/4 of the weight. Of course, mass doesn't matter. What's the radius at this point? So that's going to be, oh boy, r is the 4v squared over 3g. Yeah? 25 squared, 625. I'm going to have to go calculator here, folks. Oops. 625 times 4 divided by 3 divided by 9.8. 85 meters. What do you think? Those are what we call apparent weight problems. All right, we're not looking, I mean, the weight is what the weight is. We're looking for the force that makes you, that makes you experience your weight. We can't tell what we weigh other than the fact that we feel how hard the ground pushes on us when we stand on it. Or we can't tell what we weigh unless we have to hold onto a rope to hold ourselves up and we feel how hard we have to pull on the rope, or really how hard the rope has to pull on us. Right? So when we talk about apparent weight, we're not actually talking about weight. We're talking about the force that makes you experience that weight. Okay? Now here's a really cool, what I think is a really cool, if I can find the thing, where's my little thing? Where's that thing? My little remote, a little clicker. Here it is, in the sink. Oh, how was that sound before? Yeah, oh, not this. We'll get to this. Yeah, roller coaster loops, when you look at them, they really look like that. They're not circular, right? We had this slide back here, right, where we say, here's a roller coaster loop. They do not look circular. They really do look like this. And the question is, how come? All right? Well, let's look at forces in different spots, right? We got a weight force there. And normal force, like we said before, doesn't have to be anything, right? You can get a really great weightless feeling at the top if that normal force goes away. Here, same weight force, a normal force inward. Down here, normal force like that. Weight force downward still. Sure. Now, the force that keeps you in the seat, right, is what? Anybody? Normal force, right? We have to have the seat push on your butt. Oh, that's right. However, what we have to do, what am I trying to get at here? To keep you from, to keep you from hurting your back. Really, I mean, what we're saying is the normal force has to keep you in the seat. But if normal force gets too big, then you feel like you weigh a lot more than you do, right? Normal force here is your apparent weight. And if you feel like you weigh a lot more than you do, well, that could be literally painful, all right? If suddenly if a 400-pound person jumped on your shoulders, you would feel like you weighed a lot more than you do, and that could be painful, right? So in order to keep you from hurting your back, we have to do something with this normal force. We have to keep it as constant as we can. All right, now, like we said, we might like it up here if that normal force feels real small, right? That gives us that weightless feeling. That could be fun. People pay good money for that normal force to go away, right? People pay good money to go skydiving. No normal force acting on you. You feel weightless. At the top of that loop, we can get normal force to go away. At those, a nice little like camelback thing like that on a roller coaster, at this point here, here's mg, right? We can get it to feel like normal force goes away and we feel weightless. So much fun on that part. That part's great, right? So we pay for normal force to go away, to feel weightless. Now here, And here, we can't have it go away. We need it to provide centripetal force, but we don't want it to be too big. If it's too big, you feel like you weigh a ton, and like we said, that can be painful. So the question is, how do we keep normal force as constant as possible? Well, here's what we do. First of all, what affects how big the normal force is? Well, two things. The speed, right? We're really saying what affects centripetal force. Well, the faster you go, we know this, the faster you go, the more normal force there is. Really, centripetal force. Okay, so typically, as you went from here down to here, gravity says you're going to accelerate. You're going to go faster. As we go faster, well, that would typically make this normal force get a lot bigger, right? If we double the speed, that would give us 4 times the normal force. So from one place to another, if your speed went up by a factor of 2, your apparent weight would go up by a factor of 4. All right? Oh, yeah, right, there it is. Sure, there it is, right? There's that quadratic relationship. So how do we counteract that? Because your speed definitely might increase by a factor of 2, but we can't have that normal force increasing by a factor of 4. So what do? Well, we change this. Right? We change radius. And in order to keep, so if we look at these spots here, the top section of that track might be part of a circle that has a radius that's like that. The center part of the track might be part of a larger circle that has a radius like that. The bottom part of the track might be part of a larger circle that has a radius like that. Right? And so as your speed increases on the way down, we make the radius of that curve a lot bigger. And so these two things can counteract each other. Increase of speed would make that Fn go way up, but an increase of R keeps it down. There it is. All right, so that's literally why those loops are shaped the way they are. All right? You won't be asked about that, but it's just a great thing to, I mean, it's not a test question, but it's a really good way to look at, factors that are affecting how big the forces are. Okay? So let's see. This we'll talk about tomorrow in class. All right? And I think, what else? Just some diagrams. Yeah, so tomorrow we'll be able to do this, but you are now equipped to do all the problems on that worksheet that I gave you. All right? So all those problems on that worksheet I'd like to see tomorrow. I know it's a lot. However, I think, hang on the back, but not all of them. Yeah, the last 2 are orbital motion ones, so we don't have to do that. We already did one of them. Yeah, so these first couple are super quick, super easy. There's some car around curve ones. There's some roller coaster ones. Yeah, you should be okay. All right? Yes, I know it's a lot of work, folks, but this video hopefully wasn't too long. All right, folks, I will see you tomorrow. That's it. Please.